Again, the last week, I believe we left off talking about some of the after effects of hydroplate theory and some of the things that we think happened right after the flood. So we'll pick up there. We talked about the three phases of the flood: the eruption phase, followed by the plates sliding down and becoming completely submerged, and then the final phase where you have very high continents, very warm oceans, lots of dust in the atmosphere, and then the ice age. We hypothesized that there was only one ice age, that it may have happened in phases though. So for example, if you study the extent of the glaciers in most areas of the world, you will find, I think it's called a terminal moraine, a deposit of a bunch of rubble, basically, where the glacier is advancing across the land, and then it retreats and it leaves behind this big line of rocks and pebbles and dirt and all kinds of other stuff we identify with the maximum extent of glaciers. So we find at least two of these types of geological features in many places of the world, which of course led some scientists to stipulate that there was more than one ice age. And nowadays, I think they're up to 7 or 8 ice ages. Younger creationists think there was only one ice age, but that it perhaps happened in phases after Noah's flood. Okay, so during this ice age, you had much lower sea levels, much higher continents compared to them. And so you would have the ability to walk all over the world. People ask, what are the continents, do you think the continents were ever connected? They still are. You lower sea level by 150 feet, except for the channel that's been eroded by the ocean current between Australia and Southeast Asia. You can walk all the way from here to Tasmania or to Argentina if you prefer. So now, some people have argued the Earth is still recovering, and that's why we've seen a slight increase in the average global temperature over the last 200 years or so. And I'll remind everyone that the Earth was significantly warmer during the Roman warm period than it is today. As far as I can tell, that's an undisputed fact. So I don't know, maybe the Earth is still recovering from that, but I think our current climate has more to do with the deforestation that has happened on this planet, desertification that's happening in many places of the world. By the way, not so much in America. We have seen some of that, but there's more trees in America today than there were 100 years ago. Some people say twice as many. So, but if you look at the deforestation and the desertification, particularly that last one, that have happened over the years in Africa and places like that, you start to realize that we've lost a lot of ground cover. We've lost a lot of the forests that used to moderate the temperature, right? And so that can increase global temperature. Alan Savory calculates that roughly half of the measured increase in global temperature over the last 200 years is just due to desertification. And of course, there was another scientist who calculated that roughly half of the observed increase in global temperature is just through the massive growth that we've had in cities. It turns out that concrete and asphalt and things like that are not great ways of moderating temperature. You need a lot of trees. And so if you're curious about this, I highly recommend you look into it. There's ways you can actually design a roof that has grass on top of it, a very low pitch grass roof. And if and when humanity switches over to such a system, it will of course be extremely resistant to hail damage. So that's good. It would be quite heavy, so it'll be very difficult for storms to damage it. The problem is it's very heavy, so you have to build a very strong structure and to be able to support all of this weight. Eventually, though, we might get it figured out. We got some testing going on right now. Malarkey Roofing Products. I'm a huge fan of their company and many of their products as well. We use them all the time in the roofing world at my other job. So one of my other jobs. And so there's progress to be made in that area. And, so if you want to help reduce global temperatures, best thing to do, plant a tree, something like a Shumard oak, perhaps, that would be native to Oklahoma and does very well in our soil and climate and things like that. I've got one in my front yard, and it's doing quite well. So now, we hypothesized earlier that the Earth's environment had changed drastically. The atmosphere specifically has changed apparently very drastically since Noah's flood. We know that by looking at amber, fossilized amber, and looking at the air bubbles that are trapped in that. One of the mechanisms proposed by hydroplate theory for this change is because we have so much erupted water onto the surface of the Earth that it could have very easily absorbed a lot of the CO2 and the oxygen, for that matter, out of the atmosphere. There are also many scientists, many of them atheists, by the way, who believe that during a magnetic field reversal, which may have happened during Noah's flood, that you would get a bleed off of oxygen out of the atmosphere, which gets blasted off of here by the solar wind. So basically, our magnetic field protects us from many of the effects of the solar wind. And during a reversal, those shields are down, and basically we're exposed to direct energy from the sun and highly energized particles from the sun's surface, and that this basically causes us a lot of problems. Okay, these are all theoretical, but they are based on some pretty good evidence. Could have been a combination, could have been both, could have been neither. But this is very logical. I kind of think that both happened and changed the Earth's environment. So you had sort of maybe during the magnetic field reversal, you would have had a sudden decrease in oxygen concentration. And then with the waters erupting out of the Earth's crust, that would have been a very slow accumulation of CO2 and oxygen from the atmosphere as those waters cool off. As you're well aware, cooler waters are much more nutrient rich because they have dissolved minerals in them, and they tend to have a lot more dissolved oxygen and CO2 in them. So they support a much wider variety of living things than warmer waters do, which tend to have that oxygen and CO2 evaporate out of them. Okay, so that may be one reason why we see kind of a delay for a couple of hundred years after Noah's flood. We still live to be 400 or 500 years old there for a little while, and it's possible Job was written after Noah's flood, and Behemoth that he's talking about is a sauropod type dinosaur that is living on the Earth at that time. But these would become more and more rare as time goes on. Okay, so we certainly don't have the kind of environment that you would need to grow a large reptile, although it's possible that some of these guys have survived to the present, or maybe until the 1700s or so, when we destroyed more of their habitat. I think we talked about before that you want three things in a good theory. You need few assumptions, the smallest number of assumptions possible. You need a lot of explanatory power. You want to be able to explain lots of data, right? Data that normally wouldn't be considered related. For example, the motion of the planets and the falling of an apple. This was the brilliance of gravitational theory, that you could unite the heavens and the earth. Same laws work out there as work here, and Newton ended up mathematically demonstrating that, and so became very famous during his lifetime. One of the few scientists who ever have achieved fame during their lifetime, right? Because usually people don't appreciate you till you're gone, right? Anyway, so he's able to explain a lot, right? That made gravity a very attractive theory. Okay, so we can explain frozen mammoths. We can explain fossilization. Okay, many fossils are found in extremely well preserved states. Not all of them, okay, but some, a tiny fraction, are very well preserved. Jellyfish fossils, for example. You'd have to bury those things very, very quickly. Well, hydroplate theory explains a mechanism for mass rapid burial of these kinds of organisms. We find occasionally fossils of dinosaurs fighting each other, right? So again, they would have had to been buried very quickly. We find fossils of ichthyosaurs that are fossilized in the middle of giving birth. Sometimes stress can bring on the birthing process, and so apparently these animals were very stressed out, and many of them are found fossilized while they're giving birth. We find fossils of fish eating fish, right? So these are all examples, and we'll talk more about them when we get to the next chapter, which hopefully we'll be able to today. So we'll talk about a lot of the evidence that we have of rapid burial of these fossils, okay? We can explain that via hydroplate theory. We can also explain craters on the moon and other planets, all right? So that's pretty incredible that those craters actually came from the Earth, and therefore that they would be very, well, they're one-sided, right? One side of the moon, for example, has many more craters than the other. So these are all explanations that we can make with hydroplate theory, which is one of the reasons why we like it so much, or I like it so much. You can also use theories to make predictions, and this is the true test. It's fairly easy to figure out the answers once you already have them, right? But can you predict something that you don't know for sure? And will that prediction bear out when we discover it later on? And it turns out many of the predictions that were made based on hydroplate theory in the 80s have come to pass. We have been able to figure out that they are actually true, okay? So we talked about many of the things hydroplate theory can explain, also the origin of the comets. Comets don't tend to last very long in your solar system. Our current comet supply cannot possibly last us more than 10,000 years. They get destroyed by being close to planets or the sun, or the Roche limit of comets is way out there. So comets fall apart a lot. Okay, we talked about there being more and deeper craters on one side of the moon than the other. By the way, you can tell that an image of the moon is not a single photograph by looking at the shadows in the craters. See, I don't know how well you can see this, but there's a shadow on this side of this crater, okay? Whereas on this thing, the shadow is on the other side. See that? So a lot of times these are conglomerate photographs. You can see the shadow is on the other side of these craters. So they will put them together from a lot of different photographs. So that's why most of the pictures or the photographs you see of the moon look white and flat, right? Because during a full moon, there's not a shadow in the bottom of that crater, and therefore you can't really see it very well. So the best time to observe the moon, if you're using binoculars or a telescope, is during something that's not full moon. And actually, the smaller the area of the moon that's illuminated, the better your eyes could adjust, and the better you'll be able to see whatever you're looking at. Of course, you can't see the backside of the moon from the Earth. It's tidally locked to our planet. So, but again, we have good pictures of it. We've flown around the moon several times, and we see that there's a lot more craters on the back of the moon than there are on the front. Okay, so to me, it seems obvious that this thing has been bombarded from a single direction. The Earth erupts out, travels some distance, some of it traveling into space, and eventually much of that material is coming back down. And here we see that the far side of the moon has been blasted, whereas the near side, not so much. By the way, it was originally thought that the reason why the far side of the moon was so much more beat up than the near side was because the Earth shielded the moon, and so stuff that would have hit the face of the moon actually hit the Earth. And they figured out that that is not true. If you calculate up, you can do this calculation. I've done the math before. It's not horrible math to do, but you want to figure out how big a sphere would be if it had a diameter of the distance between a radius of the distance between the moon and the Earth. So you got to figure out the surface area of that sphere and then compare it to the disk of the Earth that would actually shield the moon from being hit. And you'll figure out that it's so much less than 1% of the surface area is hilarious. You are not shielding the moon with the Earth. The Earth is simply too far away to do anything. Okay. People thought that the gravity of the Earth, objects would pass close to the Earth, they would speed up, and then they'd slam into the moon. This is also perfect nonsense. Okay. It's a misunderstanding of how gravity works. So you have the Earth here. If you can think of it as think of space as a two-dimensional fabric. So if the Earth is sinking down into this two-dimensional fabric, it bows down towards the Earth, right? Okay, so if it falls towards the Earth like so, then as it passes the Earth, it has to go back uphill, if you want to think about it that way. And so it slows down. So you can't increase your velocity by passing something gravitationally. It will change your direction, but not the magnitude of that vector. I should say velocity is technically a direction. So I guess it does change your velocity, but it's not going to change your total energy, right? So that explanation also does not suffice, doesn't pass the sniff test of why are there more and bigger craters on one side of the moon than the other. If that's not enough for you, find more and bigger craters on Mercury. And you might ask, well, why not on Venus? Great question. Don't know. It's possible that the Earth, the moon, and Mercury were on this side of the sun and Venus was on the other side during this event. It is also possible that Venus suffers some pretty horrific erosion. That's possible. The clouds of Venus are made of sulfuric acid, so we don't really know what kind of weather might happen on the surface of Venus, but suffice it to say, initial examinations of the surface of the planet haven't really revealed much in the way of craters at all. So, that's just strange. We don't have a good explanation for that. But we do have the largest crater in the largest known crater in the universe on the surface of Mercury. Okay, it's known as the Caloris Basin. It is almost 1,000 miles wide. That'd be halfway across the United States, ringed by mountains 1.2 miles tall. Okay, in the impact, okay, you got the crater on the one side. If you travel, look at what the shock waves would have done on the other side, you get this, what we call chaotic terrain on the opposite side of the planet. And they call it the Caloris Basin because it gets so hot over there. So craters on Venus could be, Venus is on the other side of the sun. So by the time all that junk got to Venus, it was much more randomly distributed. Don't really know. But again, we can explain the craters on Mercury. Many craters on the Earth seem to be about the same age. And of course, they're using dating methods that I strongly disagree with. But to me, it's interesting that they find a concordance. In other words, all of their methods are wrong the same direction. And they find that these craters are very, very close to the same age. Many of them are very close to the same age. And this has really perplexed the scientists. Of course, I believe all of them got there during or shortly after Noah's flood. And I use that to explain why so many, for example, in the earliest art of human beings, cave paintings and stuff like that, if there's a comet that shows up, all the animals are running away from it. It's a catastrophe. Okay. So if the Earth is billions of years old, of course, you would expect craters to be randomly distributed and from random times, perhaps clustered. You might find more craters during the early Earth as a bunch of junk from space is slamming into us, but we don't find that. We find most of the craters coming from a similar age, particularly the largest ones coming from a similar age. Theologically, hydroplate explains why there was no rain before the flood. Now, isn't that interesting? The Bible says there was no rain before the flood. And of course, if you know anything about physical science, and like, wait a minute, how could there possibly be no rain? Well, you'd have to have really short mountains, extremely well-distributed amount of heat all over the planet, like Venus. Venus has almost the same temperature over the entire planet because the atmosphere is so thick. So if we had a similar kind of thing here, not that bad, but a much thicker Mo Beta atmosphere, we wouldn't have this extreme difference between the amount of heat absorbed near the equator, and the amount of heat that makes it to the North and South poles, right? So yeah, you can have a situation where dew is providing, and springs provide all the water that these plants need. All right. We explained where all the water came from for the flood, how it managed to cover the mountains, and where it all went after the flood. Okay. We explain why we don't live to be 1,000 anymore. You know, I have people that make fun of, you know, a global flood, and the Bible says the mountains were covered and all this stuff. And he'll say things like, Cartwright, are you trying to tell me that Mount Everest was covered with water? Mount Everest is 7 miles tall. Excuse me, Marianas Trench is 7 miles deep. Mount Everest is 5 miles tall, almost 30,000 feet. You're saying there was 5 miles of water on this planet? Where did it all go? We only have, you know, an average of about 2 miles of water on the planet at the moment. And of course, my response to that is, why, good sir, you should study the geology of the Himalayas. Those are sedimentary mountains made of sedimentary rock, i.e. laid down by water. There are fossils of clams on top of Mount Everest. Everybody knows Mount Everest was covered with a great flood. It's just a question of when. And here we go again with the whole, you know, we actually agree on quite a bit. We all agree Mount Everest was covered with water. The question is, how fast did Mount Everest come up out of the ground and become a mountain? Hydroplate theory says it happened very quickly. Well, it would have to, wouldn't it? Otherwise, you wouldn't find those jagged, sharp peaks. You would find heavily eroded, weathered, rounded mountains, wouldn't you? It's not what you find. And, you know, Rockies either. The Rocky Mountains are in the Alps, and many other mountain ranges are obviously young and obviously erupted very quickly up out of that terrain, which is well explained by hydroplate theory. Good luck explaining it by plate tectonics. I think we mentioned before that the entire Earth will be eroded down to sea level in a mere 14 million years. Plate tectonics just doesn't have the juice to keep pushing the mountains up. Mountains are not being pushed up fast enough to escape all this erosion. So how'd they get there in the first place? Great question. Okay, we also explained why humans, our lifespan is limited. We had a kind of a bottleneck genetically. That's not so good for your organisms. We have a difference in our nutrition levels. Perhaps our food isn't as good. We have an influx of mutations that we didn't have before with UV light, other things that might mutate our DNA and cause us all kinds of problems, right? So we can explain that. We can also explain why the flood is a one-time event. This was not a hurricane or a tsunami that happened here, okay? This was a singular event. God promised never to flood the earth again. He won't ever flood the earth again. The next destruction will be by fire, and there's not going to be an ark. The only way through that fire is by salvation. The only way out is through a relationship with Jesus Christ. Are you ready? Could be tomorrow. Might be 10 years. Might be 100 years from now. But the Lord is coming back. He's coming very soon. Okay, so we've discussed, as promised, we have some predictions we can make from this theory and that have been made. For example, hydroplate theory predicted that there would be water ice left on the moon and possibly other places in the solar system. May I suggest to you that, if a scientist had heard that back in the 80s, an atheist scientist, they would have laughed at it, okay? And here you go. When it was first reported that there was water ice left on the moon, North and South poles in permanently shaded craters, scientists were absolutely incredulous. They did not believe their instruments. they cling to their worldview just no matter what, right? They will believe what they believe despite the evidence, despite hundreds, perhaps thousands of tons of ice that are still on the moon. Okay. Now, this is impossible. That ice, if it came from comets millions and millions of years ago, that rained down on the moon or whatever, that ice would have long since sublimed out into space. Because you got to understand, the moon gets up to like 200 something degrees during the daytime. The day lasts like 2 weeks on the moon. And so even though this ice is in permanently shaded craters, you still have a lot of heat that's getting there via the crust of the moon or the surface of the moon. Okay, I don't think the moon actually has a crust. I think it's solid. Anyway, not that I've dug all the way through it or anything. So if that happens for thousands or certainly for millions of years, you're going to lose all of this ice. It will change directly from a solid to a gas and sublime out into space. And the moon doesn't have enough gravity to keep those gaseous molecules on its surface. That's why the moon doesn't have an atmosphere. Ditto for Mercury, right? If you added an atmosphere to Mercury, it would all blow away eventually because of the intensity of the solar wind, right where Mercury is, being very close to the sun, and because Mercury simply doesn't have enough gravity to hold on to those gaseous molecules in the face of the solar wind. It's a kind of a smaller planet than the Earth. So Mercury is kind of a denser, slightly more interesting version of the moon. If you've ever seen pictures of it, it's not that impressive. It's basically a very large rock. Okay. So we predicted this stuff back in the 80s, and we found it. We found that water ice that's on the moon. I would be very interested to know if it's salt water. That is also a prediction of hydroplate theory, that you'd have a significant amount of salt in that ice on the moon. Well, if that's not enough for you, then we find water ice on Mercury. This was much more recently discovered. And again, we're looking at, I forget if this is the North or the South Pole, but anyway, we're looking at permanently shaded craters on the surface of Mercury. And we notice in those shady spots where the sun never shines, you have water ice. This particular water ice, we now know, is rich in organic material. Well, who could have predicted that? Where did all this organic material come from? Well, it came from the surface of the Earth, of course. All right. Yeah, okay, so this is South Pole. South Pole is at the center of the image here for Mercury. So how's that for a prediction? That has come true. We predict that there would be no sedimentary rock or fossils underneath mammoths, that they were walking on the original Earth's surface, and there would have been no sedimentary rock underneath them. No fossil fuel either. Or really any frozen muck. If muck came from this event, then if you dig down through the layer of muck, you should hit bedrock, not sedimentary rock. You should hit granite or some other type of support for that. So far, that has proven to be true. We haven't found any. Now, it's true that we need more data on this before we can, drive a stake in the ground and declare this a victory for hydroplate theory, but so far it's all looking pretty good. Okay. Admittedly, crude geological maps of Siberia say that there should be fossils and sedimentary rock within a few miles of frozen mammoths. The region of the world is very unexplored at the moment. What accounts we do have support that the idea that there's not anything going on sedimentary rock wise under the mammoth. So we look at Tomokov. Great name for a dog, by the way, if you need one. Okay, put that one in your back pocket. Tomokov, in his chapter on geology of the Berezovka site, wrote that marine shells from marine mammals have never been discovered in deposits having frozen mammoths. Herrn von Maydell, reporting his third frozen mammoth, some of these guys are obsessed, wrote, despite my thorough search, not a single shell or fossil was found. Beneath the Fairbanks Creek mammoth sediments down to bedrock contained no marine fossils, no layered strata, no coal seams, no limestone. How about them apples? We don't have any evidence of the global flood on the ground that the mammoths are walking on. Another prediction that has proven to be true is cooled water, highly concentrated salt water underneath major mountain ranges. This particular one was published in the most prestigious scientific journal in the world, which is just called Science. It was published in 2001, and of course, they had no idea that they were proving a prediction of hydroplate theory, because of course we believe that as the plates crashed into each other, the top plate got rolled up and then it might have trapped a small amount of highly concentrated salt water deep within the mountain. Okay, and here we have a survey that is showing this. Many encouraging results, guys. I'm a big fan of hydroplate theory, but we need more data. It is true, okay? Other predictions that have been confirmed, if there are deep water channels under Bosphorus and Gibraltar, again, indicating the sea level was originally much lower, not hundreds of feet, but perhaps thousands of feet lower than it is today. Several predictions on the size, shape, and composition of asteroids. I want to really quickly just visit that, okay? So let's look at one of the most surprising things to ever have been discovered was that there are some asteroids that have moons. And this is really bizarre. Let me get a new screen share here. I think that'll work. As an asteroid should not have enough gravity to hold a moon. Where is your asteroid getting a moon from anyway? That shouldn't be possible, right? Asteroid is so unbelievably small. The idea that it captured its own moon gravitationally is statistically impossible. We found several of them, though. Several asteroids that have moons, their own moons that orbit them. Here's an example of one. This is a mile-wide asteroid with its own moon. That is so weird. How did this happen? Well, of course, they believe asteroids are leftovers from the cosmic burp that built this solar system, and that, of course, comets and things like that came from way out in the Oort cloud. You know, so the idea that maybe this is a captured comet or some kind, it's just out of the question. It's out of the question. However, if these things originated in that jet of water, remember that jet of water is eroding the sides of the crack at like unbelievable speeds, right? And the crack, the sides of the cliff there are crumbling into that jet of water. So you have these huge chunks that get thrown up out into space. Well, if you have this jet of water that propels you up out into space, you could easily have many objects that would end up orbiting one another out in space. As we see, this object has its own moon. So if they came from the same place recently, then you can have this effect. Okay, and by the way, some of these, for example, this guy, that's an artist impersonation. That is not an actual photograph. But here's an actual photograph. Asteroid 243 Ida, which is Ida, the asteroid Ida, and its moon. How about that? The asteroid's not even big enough to be spherical, and it has its own moon in a pretty close orbit too. So basically impossible to explain if you don't have hydroplate theory. Okay, we're going to go to Google here. I want to show you another thing that's impossible to explain. All right, which is the surface of a comet. Now, if this picture wasn't in black and white, let me make sure I got the right screen that I'm showing you. Yeah, okay. If this picture wasn't in black and white, let's say we put a sunset in the background, what would you think we were looking at? I mean, it looks like Arizona. Why does it look so familiar? Well, you see these roundish rocks here? We have a name for those, don't we? Those are boulders, right? Now, we know where boulders come from, okay? Boulders only come from water erosion. Just look at all of these boulders everywhere, some of them the size of trucks. This should be impossible. It should be absolutely impossible to have boulders on the surface of your comet or your asteroid. This is a comet, actually. But we find them all over the place. And I'll do you one better. Look at that. Up close picture of a comet. What do you notice about the shape of this bad boy? It has kind of an hourglass shape to it. It almost looks like two snowballs that have been kind of frozen together. Again, in hydroplate theory, if you have these objects that are being propelled up by the fountains of the great deep, it would not be out of the question at all that they would get flung out into space at very close to the same speed and direction, such as that they would freeze together in space and be preserved until this day. The idea that they have just simply eroded to have this shape is kind of out of the question. We do find several that are this shape. So, and here's another picture of the same one, I think. But you get the idea. It has this very bizarre hourglass shape to it, and it's just eerie that it really looks like two comets that have been fused together. And of course, evolutionists believe that comets come from the Oort cloud, which is supposedly thousands and thousands of times further away from the sun than we are. And so if these comets got bumped out of here by some kind of weird gravitational thing and started heading towards the sun, they have velocities in the just tens of thousands of miles an hour compared to the velocity of the sun. And if they ever got close to each, I mean, if they smashed into each, they would just obliterate one another, right? That's not what we find. We find very clear evidence that these comets were traveling at very close to the same speed and direction as well, the same velocity, very close to the same velocity, in order to come together and make this kind of a thing. And I just think it's crazy that God knew we were going to be looking at these pictures the whole time and put these comets up there just to show us that we might be on the right track here. Oh, here's another one. Here's another one of a similar kind of comet, which has been apparently made of two smaller comets. There's another one of boulders on the surface of comets. And this has just perplexed the ever-living daylights out of evolutionary scientists who have no explanation for why this should occur. Okay, so that is hydroplate theory. You have your homework slide here that you can work on for homework if you have time. I'm well aware of the fact that many of us have a very full plate this year, so I leave that up to you. And we're going to get into the second section, which is originally the third section, of course, of origins, which is the fossil record and general features of geology. Okay, so if I can hit the right button, that would really be a benefit. Let's try that one. All right, so the fossil record has been claimed to be the very best evidence that evolution has to support it, which I think is very interesting. We're going to study it for ourselves and see if it really supports evolution, or if perhaps much of the information that's gotten out into common knowledge is highly selected and pre-digested to try and brainwash people into a certain way of thinking. All right. Okay, so you got to learn a few things about fossils and geology to understand what we're talking about here. The first thing that we've got to understand is that fossils are rocks. They're mineral. The vast majority of them, anyway, are completely mineralized or dang near completely mineralized. Most of them are marine bivalves. Very few exist of anything else comparatively. Still, we have hundreds of thousands, perhaps, of tons of fossils that we've uncovered so far, and more than one has been proposed as evidence for macroevolution. Now, we've got to understand that evolution as a philosophy of origins comes in three basic flavors. Okay, we've got to talk about this in order to understand why the fossil record might be important, either to evolution or to a young Earth creation model. The first theory, hypothesis, philosophy, whatever you want to call it, not a theory, it wasn't based on very much observation, okay, was what we call Darwinism. This is what Darwin proposed in his book, okay? So its mechanism for change is use and disuse. So Darwin proposed that a horse-like thing out in the savannah would be stretching its neck out to try and get leaves out of trees, and that over thousands of years, they hadn't invented millions of years by then, this animal would grow a much longer neck, and hey presto, you have a giraffe. Okay, use and disuse. Well, that nonsense propagated widely because at the time Darwin published his book, we had no inkling of how characteristics got passed from parents to offspring, only that they were. Okay, so this was fairly reasonable and nobody could really question it on a scientific grounds. However, when genetics comes to light and to life in the early 1900s, this creates a big problem, as in mucho grande problemo, for macroevolution, evolution as a philosophy of origins or as a religion, okay? Because now this religion that you claim is so rational cannot possibly have taken place, because it doesn't matter how much you stretch your neck out, your kids are going to have average sized necks. It is determined by their genes how tall they are, right? And what the melanin concentration is in their skin and their eyeballs and their hair. And, to a large extent, what IQ they have is determined by their genetics. Something like 80% is determined by genes. How fast they can run, determined by genetics. How high they can jump, a lot of it is determined by genetics. You're not going to get a human that can jump 20 feet from, flat-footed without, the help of any kind of a machine. It's just not going to happen. We don't have the genetic information for that. Okay. So how can you change or modify the genetic information that parents pass to offspring? Well, they eventually found that there was a way to change that information by mutation. They were forced into this position, okay? And this is the one that they maintain to this day. Every government school in America teaches its biology students, and really everybody, including the teachers there, that evolution by mutation is how we got here. The mutations in our genetic code produce the fantastic variety of living things that we see on this planet. They teach it, but they don't believe it. Everybody believes that mutations are dangerous, radically dangerous, in fact. So for example, if you're exposed to asbestos, you inhale some of that, you're at a risk for mesothelioma. Why? Because asbestos has such a tiny fiber to it. It's a natural fiber. Asbestos is all natural. Did you know that? Yeah. Also, by the way, talc powder is oftentimes mined in areas that are very close to asbestos. So it is very possible to get talc powder that is contaminated with asbestos. Johnson & Johnson knew that in the 1970s and covered up that science. So most people were completely unaware of the fact that dousing themselves in talc powder was so unbelievably dangerous and would lead to cancers. My wife's aunt passed away from ovarian cancer, which was almost certainly caused by the talc powder she was continuously exposed to at her job. So don't use talc powder ever. That's just my opinion. By the way, you can get a powder that does the same thing that's made out of cornstarch. Okay. So if you're interested in that kind of thing, do your own research. Sorry, I got distracted. My point is, everybody knows mutations are bad. Okay. Mutations cause cancer. That's what cancer is. Cancer is a mutated cell that's lost its identity, doesn't know what it's supposed to be when it grows up, so it demands resources from the body. It grows and replicates like crazy. It's extremely, the more aggressive it is, the more deadly it is. And eventually crowds out your body's organs and you die of organ failure. Mutations are not just bad. They're not just painful. It's not just that they'll kill you. It'll hurt the whole time that you're dying. Mutations are unbelievably, overwhelmingly negative. We all know that. X-Men and all those kinds of movies where they show the mutation and all, now he's super strong. Perfect, unadulterated fairy tale. Right? This is good for entertainment, but it is not what people believe. You don't see these scientists sticking their head in the microwave trying to mutate their cells. You don't see them swallowing some uranium hoping that it'll mutate their cells. No, that'll kill you is what it'll do. Anyway, so this is what they teach, but they don't put this into practice. Nobody practices this religion. It would kill you. Well, so they call this evolution by mutation. Okay, so the first one was Darwinism. That's evolution by use and disuse. That's perfect nonsense because we all know that genetics limits the physical characteristics of a living thing. The second theory of Darwinism is neo-Darwinism, which just means the new Darwinism. And it says that we all got here through mutation, which is perfect nonsense as well. And I know, and you thought this would be difficult to disprove. Now, in fact, there's a third theory of evolution that is even more ridiculous than the first two. Buckle up here, folks. This could be a bumpy ride. Well, scientists have, especially those who study and specialize in geology, have this to say about the fossil record. Oh, but backing up here a little bit, let me remind us that evolution by use and disuse, Darwinism, evolution by mutation, neo-Darwinism, both of those theories require a series of very small incremental changes to happen over a long period of time in order to effect the change that they need in these organisms. So for example, you start with a dinosaur and you end up with a falcon. How? Slow, gradual processes. They say evolution is too slow to see it today. It's just, it takes millions of years for those changes to accumulate to where you can actually see the difference. And of course, that's ridiculous, but that's what they believe. Excuse me, that's what their theory of their hypothesis, their philosophy teaches. May not be what they believe. Well, so those two theories of evolution, the first two that we've talked about, require literal mountains of evidence in the fossil record, right? You'd be able to see these fossil organisms making those slow changes into the organisms we see today. For example, between a rat and a bat, between a reptile and a bird, especially, right? Between a chimpanzee and a human, or whatever the common ancestor is of apes and humans, right? You'll be able to see these kinds of changes very obviously. In fact, it should be one of our biggest difficulties digging up fossils is figuring out what they are, because it should be kind of a mix. In other words, you wouldn't be able to tell the difference between bats and rats back there because they're all kind of mixed up, and they're, this one's more like 10% bat and 90% rat, right? You just have this spectrum of variously mutated organisms that are kind of miserable back there, okay? That is not what we find. We do not find the missing links. They are still missing. Let's listen to what an expert had to say about the whole thing. As is now well known, most fossil species appear instantaneously in the record, persist for some millions of years virtually unchanged, only to disappear abruptly. The punctuated equilibrium pattern of Eldridge and Gould. This was a quote by Tom Kemp in a article he published in New Scientist, 1985. So how long have we known that there are no missing links to speak of? Most fossil species are they're there, they're fully formed, they're ready to go. A little bit longer than I have been alive, we have known this. But do you think the average school child knows this? Do you think the average biology teacher is aware of this quote by one of the top experts of his day? Do you think they even know about who Stephen Gould was? Stephen Gould was one of the greatest paleontologists to ever walk the face of the earth. And what did he have to say about the missing links? He said there's so little evidence that he came up with a third theory of equilibrium. He came up with a third theory of evolution he calls punctuated equilibrium. I probably didn't say that right. Right? Came up with a different theory. He argued that there was no evidence of evolution by mutation in the fossil record. Well, that's the whole ball game. I guess we can go home. I mean, if the evolutionist of evolutionists says that there's no evidence of evolution by mutation and certainly not of evolution by use and disuse in the fossil record, what in the name of logic and reason is he actually talking about with this punctuated equilibrium stuff? I told you had to fasten your seatbelts for this one. Okay, you ready for this? I'm going to lay it on you. Might want to be sitting down. Punctuated equilibrium, you know, what does that mean? It's like punctuation, right? A halting, abrupt, like stop, right? Equilibrium just means it stays the same. So he has interrupted sameness. In other words, one day a Tyrannosaurus Rex laid an egg and out hatched a chicken. This type of theory has been hypothesis, philosophy, whatever you want to call it. Certainly not a theory by the scientific definition of the word. This has been called hopeful monsters. Gould is arguing that evolution happens too fast to be fossilized. Except for most of the time, evolution doesn't happen at all. You call that science and put it in a science textbook? I think I'd call that a fairy tale and throw it in the garbage. Come back when you have a real argument, right? Well, you're going to have this series of small steps between these giant changes we observe in organisms. No lungs, lungs, no feathers, feathers, no circulatory system, circulatory system, no backbone, backbone. Those are some big gaps in the fossil record, right? There's no missing links between to speak of. We'll talk about a few that have been shoehorned in there between humans and apes, or between whatever common ancestor exists between humans and apes. But there's an even bigger gap than that. There's an even bigger problem, and that is the gap before the gap that we're going to be studying. That is the gap between apes and other vertebrates. There's nothing linking apes to any other type of vertebrate. There is no half ape, half whatever the apes are supposed to have evolved from. What are apes are supposed to have evolved from anyway? They don't talk about it, do they? You've never heard that discussed by any kind of paleontologist or evolutionary scientist at all, because they have an embarrassing lack of evidence for this idea that they're trying to say is some kind of science. In other words, they don't have any of these steps, not even one, but the vast majority of what should be intermediate forms. Okay, they don't have a single step. In other places in the fossil record, they try, some of them try to say that they do have intermediate forms. We'll talk about a few of them as we get further into the subject material. So, what is a fossil? Ah, yes, fossils form slowly over millions of years. Not really. Well, we're going to define fossil as the remains of a once living organism, and you can have lots of different types. There are 4 major types of fossil. The fossil can tell us something about the past, but it's not telling us the whole picture. We get a part of its skeleton most of the time. I think something like 80% of all fossils are less than 1 bone. So finding a complete skeleton of anything is very, very rare in the fossil record. Okay, so we don't have the whole picture. Fossils are exceptions to the general rule that when things die, they decay. The carbon cycle, right? Most common type of fossil is what we call a mold cast. If you've ever seen the the multiple billions probably fossils of marine bivalves, clams, and things like that. These are a type of a mold cast. So the clam is sitting underneath the ocean. He gets buried in Noah's flood. The clam completely decays away and leaves behind a mold, which in most cases will fill up with a cast. Okay, so it's important to realize that these types of rock layers are not, and I want to emphasize this, they are not waterproof. Sedimentary rock is not waterproof. It is heavier when it's wet. Sandstone is 20 some odd percent air. Okay, so water can percolate down through these sedimentary layers and they will fill it in with a finer type of sediment, which will make a cast over time. Okay, it's completely inorganic. There's nothing but mineral left behind. All the mineral of the organic parts washed away thousands of years ago, probably, in my opinion. And they're extremely common. Marine bivalves make up a huge fraction of all fossils. Maybe 60, 70, 80% of all fossils are marine bivalves. Okay. Clams, and more clams. Okay. As is the case with all types of fossils, these are only a small fraction of the organisms that lived. So most of the clams didn't get to make a mold cast. They died, right? Second type of fossilization is petrification. In this case, we actually have some of the original organic material. It's just been converted into a mineral. Very common with, or I shouldn't say common, but one of the most common types of fossils that we find is petrified wood. We see lots of petrified wood, and they are more likely to be petrified. And oftentimes we have details here preserved that we wouldn't otherwise have, like the rings of a tree or something like the color of the tree is left there because some of these organic materials get, as I say, mineralized. Okay. Sometimes this process can happen very quickly and preserve some organic remains within the fossil. And we used to say, by the way, that it only happened with well-preserved fossils, but now we know that organic remains and fossils are far more common than anybody suspected. Even the young Earth creationists did not expect to find so much evidence of recent burial as we find. We'll maybe investigate the link below later on. You're looking for red blood cells in T-Rex bones by Mary Schweitzer. The Schweitzer is, I think, the American pronunciation of her name. She is the first person, she's an evolutionist, by a Christian, but an evolutionist, I know, that discovered red blood cells in these T-Rex bones that she was transporting. And they're fairly well preserved, but they are not petrified. They are actually a mold cast type of fossil. Although maybe some of it's petrified. I forget the details. You look it up for yourself. The third type of fossilization is carbonization. And I want to emphasize that carbonization can happen very rapidly. Excuse me. So let's look at how this process can take place. So we're oftentimes told that fossil fuels form very slowly over millions of years. And let me suggest to you that that's perfect nonsense, okay? You can take any carbon-based molecule and turn it into a collection of fossil fuels. Okay, so for example, well, let's just look at, you just add heat and pressure, basically. Add heat and pressure, you can turn it into fossil fuels. Okay, there's a little graph down here. Up, maybe not, maybe they changed it. Well, dagblasted. Well, you can see here, you have biomass. Okay. Now these are oftentimes already being recycled. So, however, you can create a very high quality or high energy fuel with biomass used as your feedstock for your thermal depolymerization. Plastic wastes. Now, you might say, well, let's recycle the plastic. Something like 90% of the plastic that could be recycled in the United States is not recycled in the United States. And it's not because we're trying to hurt the environment. It is because plastic is basically almost impossible to recycle. Okay. And we use so much oil that plastic, it's actually in many cases cheaper to just make new plastic than to recycle the old. Plastic to fuel. What if you change it into fuel? Historically been suggested as economically viable due to the cost of collecting. Excuse me. You do have to collect the plastic. Well, we kind of already are with our garbage collecting, right? So if instead of just going out and sorting through the plastic, what if we just put a mismatch of fuel sources into our thermal depolymerization machine? In other words, we just put all of our carbon-based waste in one trash receptacle, and I don't know, the green one, let's say, and that was picked up and taken to our electricity generation plant, just using it as an example. It was burned to produce electricity. And you might be really worried about all of the toxins that we'd be releasing into the atmosphere. Well, we can scrub those out of the emitted material before we let it off into the atmosphere. So in other words, we know where it is, and we can treat that exhaust before it gets out of the atmosphere, and thereby, I mean, instead of burying it in a landfill somewhere where it may seep down into the groundwater, we have control over it. Okay, you might be worried about the production of CO2. Well, guess what? Landfills produce CO2. They do. And methane. Methane is worse. If you're worried about global warming, which I'm not, but some people are, you don't like landfills. Landfills are the bane of your existence. So again, if we use this to burn for energy, and let's take the CO2 and pump it after it's cooled down a bit, pump it into a greenhouse and grow our food with it. CO2, of course, is plant food. That's where they get their carbon for photosynthesis. So there's a way to design a system, I think, that works for everybody here. And it would drastically reduce the amount of stuff we're putting in our landfills and the kinds of problems that we have with that. We're already collecting the garbage. How hard would it be to say, okay, metals, glass, carbon-based stuff, and then maybe, you know, your batteries and stuff are hazardous waste, which of course you want to recycle those anyway. Those are valuable to be recycled. So anyway, so thermal depolymerization is a fancy way of thermal, meaning heat, depolymerization. Okay, you're taking a really big molecule and then making it into the small ones. So for example, a really long chain starch could be busted up into a molecule that's much more like octane, for example. So it is possible to make your own fossil fuels. Australia has been doing it for decades. There's a plant in, I think it's Carthage, Missouri, that is converting these kinds of wastes into fuels. So no, it doesn't take millions of years. You can do it on demand in many cases, and that might be economically viable. All right, so this week I want you to get a hold of that homework if possible, and also to maybe get a start looking at some of the stuff in the fossil record. All right, see you later.